FLiBe is a molten salt made from a mixture of lithium fluoride and beryllium fluoride. It is both a nuclear reactor coolant and solvent for fertile or fissile material. It served both purposes in the molten salt reactor experiment. The 2-to-1 mixture forms a stoichiometric compound, Li2BeF4, which has a melting point of 459 degrees Celsius, a boiling point of 1430 degrees Celsius, and a density of 1.94 grams per cc. Its heat capacity is 4,540 kilojoules per cubic meter, which is similar to that of water, more than 4 times that of sodium, and more than 200 times that of helium at typical reactor conditions. Its appearance is white to transparent, with crystalline grains in a solid state, morphing into a completely clear liquid upon melting. However, soluble fluorides such as UF4 and NiF2 can dramatically change the color salt in both solid and liquid state. This made spectrophotometry a viable analysis tool, and it was employed extensively during the MSRE operations. The eutectic mixture is slightly greater than 50% BeF2 and has a melting point of 360 degrees Celsius. This mixture was never used in practice due to the overwhelming increase in viscosity caused by the BeF2 addition in the eutectic mixture. BeF2, which behaves as a glass, is only fluid in salt mixtures containing enough molar percent of Lewis base. Lewis bases, such as the alkali fluorides, will donate fluoride ions to the beryllium, breaking the glassy bonds which increase viscosity. In FLiBe, beryllium fluoride is able to sequester 2 fluoride ions from 2 lithium fluorides in a liquid state, converting it into the tetrafluoroberylation BeF4-2. Chemistry. The chemistry of FLiBe, and other fluoride salts, is unique due to the high temperatures at which the reactions occur, the ionic nature of the salt, and the reversibility of many of the reactions. At the most basic level, FLiBe melts and complexes itself through. This reaction occurs upon initial melting. However, if the components are exposed to air, they will absorb moisture. This moisture plays a negative role at high temperature by converting BeF2, and to a lesser extent LiF, into an oxide or hydroxide through the reactions. And, while BeF2 is a very stable chemical compound, the formation of oxides, hydroxides, and hydrogen fluoride reduce the stability and inertness of the salt. This leads to corrosion. It's important to understand that all dissolved species in these two reactions cause the corrosion, not just the hydrogen fluoride. This is because all dissolved components alter the reduction potential or redox potential. The redox potential is an innate and measurable voltage in the salt which is the prime indicator of the corrosion potential in salt. Usually, the reaction is set at 0 volts. This reaction proves convenient in a laboratory setting and can be used to set the salt to 0 through bubbling a 1-to-1 mixture of hydrogen fluoride and hydrogen through the salt. Occasionally the reaction is used as a reference. Regardless of where the 0 is set, all other reactions which occur in the salt will occur at predictable, known voltages relative to the 0. Therefore, if the redox potential of the salt is close to a specific reaction's voltage, that reaction can be expected to be the predominate reaction. Therefore, it is important to keep a salt's redox potential as far away from reactions which are undesirable. For example, in a container alloy of nickel, iron, and chromium, the reactions of concern would be the fluorination of container and subsequent dissolution of these metal fluorides. The dissolution of the metal fluorides then alters the redox potential. This process continues until an equilibrium between metals and salt is reached. It is essential that a salt's redox potential be kept as far away from fluorination reactions as possible, and that metals in contact with salt be as far away from the salt's redox potential as possible in order to prevent excessive corrosion. The easiest method to prevent undesirable reactions is to pick materials whose reaction voltages are far from the redox potential of the salt in the salt's worst case. Some of these materials are tungsten, carbon, molybdenum, platinum, iridium, and nickel. Of all these materials, only two are affordable and weldable: nickel and molybdenum. These two elements were chosen as the main portion of haste alloy N, the material of the MSRE. Altering the redox potential of FLiBe can be done in two ways. First, the salt can be forced by physically applying a voltage to the salt with an inert electrode. The second, more common way, is to perform a chemical reaction in the salt which occurs at the desired voltage. For example, redox potential can be altered by sparging hydrogen and hydrogen fluoride into the salt, or by dipping a metal into the salt. Coolant. As a molten salt, it can serve as a coolant which can be used at high temperatures without reaching a high vapor pressure. Unlike sodium or potassium metals, which can also be used as high-temperature coolants, it does not violently react with air or water. FLiBe salt has low hygroscopy and solubility in water. Nuclear properties. The low atomic weight of lithium, beryllium, and to a lesser extent fluorine make FLiBe an effective neutron moderator. As natural lithium contains 7.5% lithium-6, which tends to absorb neutrons, producing alpha particles, and tritium. Nearly pure lithium-7 is used to give the FLiBe a small cross-section, e.g., the MSRE secondary coolant was 99.993% lithium-7 FLiBe. Beryllium will occasionally disintegrate into 2 alpha particles and 2 neutrons when hit by a fast neutron. Applications. In the liquid fluoride thorium reactor, it serves as solvent for the fissile and fertile material fluoride salts, as well as moderator and coolant. Some other designs use it as coolant, but have conventional solid nuclear fuel instead of dissolving it in the molten salt.